Imagine a place colder than the emptiness of space itself. Not somewhere far away in a distant galaxy, not hidden inside a black hole, but right here, created by humans. A place so cold that the very concept of temperature begins to lose its meaning. A place where motion itself almost disappears. To understand how something on Earth can become colder than space, we first need to understand just how cold space really is. When most people think of space, they imagine freezing darkness, and they're right, but not in the way you might expect. If you were floating far away from any star in the vast emptiness between galaxies, the temperature around you would be about minus 270 degrees Celsius. That's only about 3 degrees above absolute zero. Absolute zero is the coldest temperature that can exist in our universe. It's not just a number, it's a boundary, a limit set by the laws of physics themselves. At absolute zero, something incredible happens. All motion stops. Every atom, every particle, every tiny vibration, gone. Matter doesn't feel cold anymore. It simply stops moving. But here's where things get interesting. Even in the cold vacuum of space, things are still moving. Tiny particles vibrate. Energy still exists. Space is not perfectly still. Which means space is not the coldest place possible. And that raises a strange question. If space isn't the coldest place, then what is? The answer takes us away from distant galaxies and brings us back to Earth, into the world of advanced physics laboratories. Inside these labs, scientists are not trying to heat things up. They're doing the opposite. They are trying to remove energy, to slow things down, to bring matter as close as possible to absolute zero. But cooling something to these extremes is not like putting ice in a freezer. You can't just chill atoms. You have to control them, manipulate them, and most importantly, slow them down. Because temperature is not really about heat, it's about motion. The faster atoms move, the hotter something is. The slower they move, the colder it becomes. So, if you want to create the coldest place in the universe, you need to slow atoms down to almost zero motion. And to do that, scientists use something that sounds completely unexpected: lasers. Normally, we think of lasers as something that burns or heats, but in physics labs, lasers can actually be used to cool things down. This works because light carries momentum. When a photon, a particle of light, hits an atom, it gives it a tiny push. Now imagine firing lasers at atoms from all directions. Each photon nudges the atoms, slowing them down, little by little. It's like trying to stop a moving object by gently tapping it over and over again until it loses all its speed. This technique is called laser cooling, and it allows scientists to bring temperatures down to incredibly low levels, far colder than anything naturally found on Earth. But even laser cooling has its limits, so scientists go even further. They use magnetic fields to trap these atoms in space, holding them in place like an invisible cage. Then they begin removing the fastest atoms from the group. This might sound strange, but it works just like evaporation. When hot liquid evaporates, the fastest molecules escape first, leaving behind cooler ones. Scientists apply the same idea to atoms. By removing the most energetic particles, they leave behind only the slowest, coldest atoms. This process is called evaporative cooling. With these methods combined, scientists have reached temperatures just billionths of a degree above absolute zero. That's not just cold, that's almost unimaginable. At this point, something truly strange begins to happen. Matter starts to behave in ways that completely defy our everyday experience. At normal temperatures, atoms act like individual particles. They move independently, they collide, they bounce around. But at ultra-low temperatures, that changes. Atoms begin to lose their individuality. Instead of acting like separate particles, they start behaving like waves.
And not just any waves, but synchronized waves. They overlap, they merge, they act as one. This creates a new state of matter called a Bose-Einstein condensate. In this state, thousands or even millions of atoms collapse into a single quantum state. It's as if they all become one giant atom, one unified entity. Imagine a crowd of people all moving randomly in different directions. Now imagine that same crowd suddenly moving perfectly in sync, as if they were a single organism. That's what happens at these extreme temperatures. And here's where things begin to feel almost unreal. Because in this state, the rules of classical physics no longer apply. Quantum mechanics takes over. Particles can exist in multiple places at once. Waves of matter can interfere with each other. Reality becomes fuzzy. And the colder it gets, the stranger it becomes. To push these experiments even further, scientists took them off the planet. They sent them into space. On board the International Space Station is a facility known as the Cold Atom Lab. In microgravity, atoms can be controlled for longer periods of time. They don't fall, they don't settle, they float. This allows scientists to create even colder temperatures and study these strange quantum states in greater detail. Inside this lab, clouds of atoms are cooled to temperatures so low that they barely move at all. They drift slowly, almost frozen in time. And in this environment, scientists can observe phenomena that are impossible to study on Earth. They can watch how quantum waves evolve. They can test theories about the nature of matter. They can explore the boundary between classical physics and quantum physics. And every experiment brings new discoveries. But this isn't just about curiosity. These ultra-cold experiments have real-world applications. They're helping us build better technologies, more precise sensors, more accurate navigation systems, and perhaps most importantly, quantum computers. Quantum computers operate using the principles of quantum mechanics. Instead of bits, they use qubits, which can exist in multiple states at once. This allows them to solve certain problems far faster than traditional computers. And ultra-cold atoms are one of the key ways scientists are developing this technology. But beyond technology, these experiments help us answer some of the biggest questions in science. What is the true nature of reality? How does the universe behave at its most fundamental level? And how did everything begin? By studying matter at near absolute zero, scientists are essentially slowing the universe to observe it more clearly. It's like watching a fast-moving scene in slow motion. Details that were once hidden become visible. Patterns emerge. New behaviors appear. And with each discovery, we get closer to understanding the universe. But no matter how advanced our technology becomes, one rule remains unbreakable. Absolute zero cannot be reached. It's a limit, a boundary that cannot be crossed. We can approach it, we can get incredibly close, but we can never fully reach it. There will always be a tiny amount of motion left, a tiny trace of energy that refuses to disappear. And maybe that's what makes this journey so fascinating, because there's always something just beyond our reach, a final step we can never take, a mystery we can never fully solve. But even though we know that, we keep trying, we keep pushing, we keep exploring, because every step closer reveals something new, something unexpected, something that changes the way we see reality. So the coldest place in the universe is not a distant corner of space. It's not hidden in a dark nebula or a frozen planet. It exists because we created it, in laboratories, in orbit, in carefully controlled environments where the laws of physics are pushed to their limits. A place where atoms nearly stop, where matter becomes a wave, where reality itself begins to blur. And in that extreme cold, we are not just studying temperature, we are studying existence itself. Because sometimes, to understand the universe, you have to slow it down, almost to a complete stop.